Thank you. Right. So just to recall, I was talking yesterday about Reed's conjecture. So from what I was saying yesterday, what can we say? That Reed's conjecture is true for surfaces with k squared lesser than 3 chi, and for surfaces with k squared lesser than 4 chi, having irregular étale covers. So I recall Reed's conjecture was that the fundamental group of a surface with k squared lesser than 4 chi is a finite extension of the fundamental group of a surface of a curve for the algebraic fundamental group. So to prove the full, from what we saw yesterday, to prove the full conjecture, one would need to prove that the surfaces with 3 chi lesser or equal than k squared lesser than 4 chi that have no irregular étale covers have necessarily finite fundamental group. Okay, we don't know, basically. We don't have any example with the infinite fundamental group and the surface. And this is open, and the methods. Okay, I'm not going to enter into this. This is also related with the conjecture on quadrics on the dimension of the intersection of quadrics that contain the canonical image of a surface, but I'm not going to enter into that. So this is just to recall. And now to answer. Yesterday, some people asked me about the topological fundamental group. I really don't know so much because I've been looking at the algebraic. That's the one I can control. Anyway, Shougang. So yesterday we had this exact sequence when we have a fibration. Pi1 of f goes to pi1 of the surface, goes to some group that will be just the pi1 of the basis of the fibration. If there are no multiple fibers. Shougang also proved for the normal fundamental group that we have a fibration with general fiber hyperelliptic, okay? Then in a function of the slope, if g equals 2 and the slope is lesser than 3.4, and or g bigger than bigger or equal to 3 and the slope lesser than 4 minus 1 over g minus 1, then the image of this pi1 of the fiber into pi1 of S is trivial. So this in particular, when you are inside within these numbers and your fibration has no multiple fibers, gives that the surface is simply connected. I'm not going to develop. So some of the surfaces I talked about yesterday, you just can work out if they have genus 2 fibrations, genus 3 fibrations. You can work out the conditions for them to be simply connected. Okay, if they have no irregular covers, no multiple fibers. So I'm not going to develop that, but anyway, that's about what I know for the fundamental group. So this is in a paper of Shougang called something like pi1 of elliptic and hyperelliptic surfaces. So So now I'm going to talk about what I promised yesterday. What are the finite fundamental groups that can occur for, or at least limitations on the order of the finite fundamental groups that can occur for k squared less than 3k minus 1, less or equal. So the first theorem says the following, that if k squared is less than 3k, the order of the algebraic fundamental group is at most 9. So this it's already a big limitation. And furthermore, if the order is 9, then S is a Campedelli surface. So what are Campedelli surfaces? Are very famous surfaces that have PG equals 0, Q equals 0, K squared equals 2. They are, maybe I should say, numerical Campedelli. So the first example of a Campedelli surface was due to Campedelli, and it's obtained as a cover of P2 ramified on with branch curve, a curve of degree 10 with 6 of these so-called 3 points. So it's triple points that have, after blow up, are still a triple point. So the so-called also infinite linear points. And that one, I think, has algebraic fundamental group Z2 to the cubed. And okay, and so those are sometimes called Campedelli surfaces, and other surfaces with k squared 2pg equals 0, numerical Campedelli surfaces. There is also there is also the other version where that's what I'm using. K squared equals 2 and pg 0 is called a Campedelli surface, and the original one from Campedelli, classical Campedelli surface. So, okay, and now this characterization, if pi 1 is 9, then Campedelli comes with a very explicit description that allows us to say that the normal fundamental group is also of order 9. Is the same. Yes. We don't know. We don't know. It depends on the, no, we don't, it's not known. What happens lots of times, especially with this small invariants, is that if you have finite algebraic fundamental group, you manage to construct the algebraic universal cover, and then because if you have a very explicit description, and you can say, let's say, for instance, if your cover is like a smooth complete intersection, you know that smooth complete intersections have in PN have trivial topological fundamental group. So then you can say, and you obtain this as a quotient by a finite group. So you also can say that your group, you know the topological fundamental group. But otherwise, it's completely open. It's open. It's even open if the topological fundamental group, no, if the algebraic fundamental group is trivial, whether the topological fundamental group has to be trivial. That's an. Yeah. 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 No, I don't know. Okay. No, but Toledo. Okay. okay, we can talk about it after. So this is the first limitation. And now if you get the range even smaller, so if you go to 1 down, the order is going to be less or equal to 5, and now we have a similar description. If the order is fine, then k squared equals 1, pg0, S is a Godot surface. Okay, these are the classical Godot surfaces. So these are quotients of a quintic surface in P3 by the action of Z5. So they are also the fundamental group and the algebraic fundamental group coincide. So this is then we have if k squared is less than 3k minus 2, we will have either the unique fundamental groups that can occur are Z2 squared, non-trivial, and Z3, but Z3 for a very restricted, for k squared equals 3k minus 3, and just for characteristic 2, 3, and 4. And that's it. And okay, and if k squared, and for k squared less than 3k, you can also say what is if the order was at most 9, but for order 8, we have again the same thing, that k squared is 2 and pg0. And I must say also, this Campedelli surfaces with a fundamental group of order 8 were studied by Miles Reed. And so the universal cover is a complete intersection of 4 quadrics in P6, and you know what, you have examples for all the things that can happen. So now I wanted to say the bounds are effective. So we have Campedelli surfaces with order 8 or 9, with a fundamental group of order 8 or 9. We have Godot surfaces with fundamental group Z5. There are examples of surfaces k squared equals 3k minus 3, and the fundamental group Z3. Those with chi equals 2 were completely studied by Marukami. I think also those with chi equals 3, but I was not sure, and I just thought yesterday, and I didn't have maths yet. So, but anyway, there are examples for 2, 3, and 4. And then for k squared less than 3k, and these pi 1 Z2, Z2 squared, it's quite easy to construct them. And basically what you do is you find suitable hyperelliptic fibrations. For instance, you try to construct genus 3 fibrations with 2 double fibers or 3 double fibers. If you have 2 double fibers, you can find Z2 torsion. You have 3 double fibers. You find Z2 squared. So okay, and these for double covers, finding these double covers of ruled surfaces is more or less, you have to find the branch locus that they are suitably tangent to a fiber. So that with some okay, and Okay, as I was saying, all the groups of order 8 or 9, except for all groups of order 8 or 9, except D4, there are examples of Campedelli surfaces with that fundamental group. And D4 cannot occur, and from the constructions, one obtains that the algebraic fundamental group is the fundamental group. So that's the general picture. So now, how does one prove these things? Well, more or less, more of the same that we have already explained. So I need again the Castelnuovo inequality that tells me that if k squared is less than 3pg minus 7, then the canonical map is 2 to 1 onto a ruled surface. That in the case we are looking at where all the covers I'm considering are regular, it means a rational surface. The Bouville lemma that any group acting freely on a surface with canonical map 2 to 1 on a rational surface must be Z2 to the R. That's the other that I explained yesterday. Now a new theorem. I wrote there Xiaogang because that's the precise formulation, but really this is also a result of Miles-Reed. So the result says that if you have a regular minimal surface of general type such that the canonical map is 2 to 1 onto a rational surface, then if k squared less than 3 chi of y, ky squared less than 3 chi of y minus 15 and ky bigger than 22, or if ky squared less than 3 times chi minus 43/8, then there is a unique vibration y to p1 with hyperelliptic fibers of genus less or equal to 3. Okay, so this is... so I don't know whether we remember yesterday why do I'm interested in this, because yesterday I was explaining that when you have some surface with a group acting and you have an invariant pencil for this group action, then the pencil goes down to the quotient. So the quotient surface still has a pencil, and sometimes, and we can discuss a bit what is the order of the group. So what is the idea behind this? It's just if the canonical map is 2 to 1 onto a rational surface, and you can limit the degree of the rational surface and find what is the degree of a pencil of rational curves on this rational surface. Then you have the map 2 to 1, and you have a limitation of this pencil is induced by the pencil of smallest pencil of rational curves of smallest degree in this rational image, and you pull back and you find this. And for this range of invariants, you find there is this unique vibration. So, so about this, it's very nice, with a very nice paper of Miles-Reed on called, I think, Surfaces of Small Degree, that is a really beautiful paper, and you will understand this thing there. So, and now I recall, now I have the genus 3 vibration, and I recall that lemma I explained in the end yesterday that says that if you have surface with a free group action, and you have a G invariant free pencil of curves of genus less or equal to 4, then only Z2 squared and Z2 can occur if G is 3 and Z3 if G is 4. So that's the okay, this is a very simple lemma, but very, very useful. So, what is the general strategy to prove this theorem? So remember that all these theorems have to do with a surface that has that we know has a finite fundamental group. We want algebraic fundamental group. We want to limit the size of the group. So, and I know that these étale covers are all regular. So what do? I take an étale cover of some degree d, and then I study what can be this surface y that covers. And then in many instances, I study what is the canonical image of y, and I find that my surface has a nice G invariant fibration, and then I can limit the size of the group G. So, let me say that if there was a way for this surface between 3 chi and 4 chi also to produce vibrations of relatively small genus, it might be possible to limit the group, but I don't know. So let's look at a sketch of proof of this first one about the Campedelli surfaces. So I want to show that if k squared is less than 3 chi, the order is less or equal to 9, and then that's the first thing. And then I want to characterize what is order 9. So what my hypothesis is that I have a surface with k squared less than 3 chi that has no étale irregular curves. And now I consider Galois étale cover with Galois group G of order D. Because this is étale, the invariants just multiply. So what do I get? I get ky squared equals d times ks squared, chi of y d times chi of s, q of y is 0, and ky squared will be less or equal because chi s is less or equal than 3 chi s minus 1. We get chi y squared less or equal than 3 chi y minus d. And because q equals 0, I can write this as 3 pg of y minus d minus 3. Okay? So I'm going to start to limit d. So first thing I want to show is that d is not bigger. That d is 10 or less. So okay, what happens if d is bigger than than 10? Ky squared is less than 3pg minus 7. So the magic Castelnuovo inequality gives you the map 2 to 1 onto a rational surface. Okay, but then we know that G must be Z2 to the R, and because I'm assuming D bigger than 10, it must have, R must be bigger or equal to 4. So D is bigger or equal than 16. squared on a genus 3 pencil, like that. If you have the pencil that's invariant. So, so we have a contradiction. So d bigger than 10 does not occur. Now we go to d equals 10. What happens? In that case, again, the same. Okay, if d is 10, the group cannot be Z2 to the R because of cardinality. And so necessarily, the canonical map must be birational, because otherwise G would be Z2 to the R. And so, but if the canonical map is birational, you must have ky squared equals 3pg minus 7 and k squared equals 3k minus 1. And now we are very lucky because this surface is, as it is usual in surface theory, any surface that is in the boundary of something. So 3pg minus 7 is the surface with the smaller invariants that have canonical map birational. Usually these things near lines, near break lines are classified. So that's, and in fact, by work of, well, first Castelnuovo, Harris, and Ashikaga Kono, these surfaces have a genus 3 fibration over P1. I could have been much more precise. What happens here is that you take the intersection of the quadrics that contain the canonical image. You find that it's a threefold of minimal degree. And then you, and that the surface Y is cut on this threefold by a relative quartic, and so that's how you know what are the threefolds of minimal degree, so you can classify them. And then you can check that this genus 3 fibration, because of these very explicit of the very explicit form, is G invariant. And so we have the same contradiction as before, because I mean this is the key thing. If you have a G invariant fibration of genus 3, you can have Z2 or Z2 squared acting, nothing else. So we get a contradiction, so D cannot be 10. So now, next, we look at D equals 9. Okay. If D equals 9, the same thing, we get ky squared equals 3pg minus y. As before, the canonical map is birational. And again, okay. Now, Kono classified also these surfaces with k squared equals 3pg minus 6. There are, so these, we have still the same situation when the canonical map is birational. You have the canonical image is contained in a threefold. That's the intersection of the quadrics through the, but the threefold may not be of minimal degree. Anyway, from the classification he has, we know that I think if ky, yes, is bigger than 17, by results of Kohn, we can, again, looking at the very precise description of these surfaces, you can find that Y has a G invariant fibration with general fiber of genus 3. And again, we find a contradiction. So this means that if KS is bigger than 1, then you don't have these, the order 9 cannot occur. So now we are left with the case of we want to see what happens if we have order 9. That's only possible for chi equals 1. Okay, Campedelli surfaces with a fundamental group of order 9. There were 2 examples in the literature. I think one due to Xiaogang, or maybe not even in the literature, because I believe one of them has been, Professor Kuhn told us about it. And I don't know whether it what was written somewhere. There was an example in Chinese. Which? No. The one with, no. I don't know. Okay, never mind. Actually, I don't think so, but I don't remember. Anyway, and then there was another, well, anyway, that's, so there are examples, and we want to see we want to find all the surfaces that satisfy this. So again, we are very lucky with this very precise description of the surfaces. So I take, I know now that my surface S is a Campedelli surface, PG0 K squared 2. I take the order 9 étale cover. This is a surface with K squared 18, PG8, and the canonical map of the surface must be birational by everything we have seen before. And now we study this canonical image. And using this classification of surfaces by Kono, it's possible to see, and the fact that we have this action, that the intersection of the quadrics of P7 containing Y is a normal threefold T of degree 6. This is the so-called threefolds of delta genus 1. And there is a cubic hypersurface that I don't know why I separated, sigma of P7, such that Y, well, the canonical image of chi, is intersection of this threefold with sigma. And now there is a very precise classification by Fujita of varieties of delta genus 1. And one looks at the possible group action and so on, and okay, very precise description, and you can find out what are these threefolds. So one is the Sega embedding of P1 cross P1 cross P1, the other that we called type A, and that has fundamental group Z9. Then there are 2 different types. Type 1 is just the projectivized tangent sheaf of P2 embedded in P7 via the tautological, and the other is the cone in P7 over the smooth del pezzo surface of degree 6 in P6. So, okay, and this very precise description of the group action of everything allows us to describe, I'm not going to go into details, but to describe completely the moduli space of these surfaces. So you get 2 connected components, one for the groups of with pi 1 Z9, and the other one for the surfaces with pi 1 Z3 squared. These surfaces were, okay, no, this is outside the the theme of this talk, but anyway, it was very nice, again, coming from the precise description we have. We found the first examples of surfaces with k² bigger than 1 that have base points for the bicanonical map. So it's a theorem that for PG bigger or equal than 1 or k² bigger than or equal to 5, the bicanonical map of minimal surface of general type has no base points. But when k² equals 1, PG equals 0, the bicanonical system is just a pencil. It has base points. And then we have k² 2, 3, 4 that we don't know. And now for k² equals 2, now for some years now, because this is old work. For k² equals 2, we have these examples. So it goes on being very challenging to find out whether there are base points for k² equals 3 or 4 in PG equals 0. It would be nice to prove or disprove that anyway. And okay, and again, the construction, it's possible to find in both moduli spaces, you find a nice cubic hyper. So these surfaces were obtained by, as I explained before, by cutting these 3 folds by a nice cubic hypersurface. So by a cubic hypersurface, so you can find nice cubic hypersurfaces that correspond to simply connected, topologically simply connected. Now you can, yes, you can find. Sorry. You can by the description find that the topological fundamental group is also 9. So finding that this cover is topologically simply connected. Okay. So okay, now I'm not going to do this proof of this next theorem that was characterizing with k² lesser than 3k minus, when k² is lesser than 3k minus 1, that the order of the algebraic fundamental group was less or equal to 5, and then 5 is a Godot surface. It goes along similar ideas, although as usual, then you have to do some more twists for one thing or other, but it's basically the same thing. And okay, and the other theorem 3 about k² lesser than 3k minus 2 was is again the same thing, that says that the only groups that occur are Z2, Z2 squared, and Z3 is again the same thing. You always take your cover, you produce in the cover, either you produce a genus 3 fibration that's G invariant and you limit the thing, or maybe you have this genus 4 fibration, but again using the theorem of Xiaogang, and you can limit the thing, or then it fails at a certain point for k equals 1, like here, and then you find, and then there are the Godot surfaces, and then you study the ones with chi, and you find it's exactly what they should. Well, for this one, we didn't have to study because it was known exactly what was the Godot surface with the fundamental group Z5. So it's always the same. Then finally, there was this characterization that if the fundamental group had order 8, then we always also had k squared equals 2 and pg 0. So that S would be a Campedelli surface. And here, again, so how do you do this? You do the same thing. You take the tall cover with Galois group of order 8. You take the invariance of y. Now, what is the problem? Is that ky squared is 3pg minus 5. And the problem here is that the surface with k squared equals 3pg minus 5 are no longer classified. So you cannot have so many. However, so we had to look a bit more closely to the surface. Using the fact that we have this action of a group of order 8, we could see that necessarily the map, that the canonical map, we have just these two options. It is birational, and the canonical system has no base point. Or the canonical map has degree 2, and the image is a rational surface. So to prove the theorem, what we needed to show, want to show, is that the first case corresponds to chi of S equals 1, and the second case does not occur at all for this cover. Okay. Now, these canonical surfaces with k squared 3pg minus 5 are not classified. This because, anyway, using the same methods of Castelnuovo theory and the theorem of Chiliberto that extended, we could show that if in this situation, if PG was bigger than 14, the intersection of all the quadrics containing the image of phi would be a normal rational scroll of dimension 3, and the scroll structure induces on Y a pencil F of genus 3 curves without base points. And the F is G invariant, so by the definition via the canonical map, again one looks at the action of G on F, and the group cannot be Z2 Z2 squared, so PG of Y is lesser than 14. This means chi of Y lesser than 15, and because the group is genus 8, this means chi S equals 1. Now, phi 2 to 1 on the rational surface. This was more complicated because, I mean, all these, because the limitations of genus were not very easy. So in here okay, if phi is 2 to 1 onto a rational surface, I know that the group of order 8 must be Z2 cubed by the Beauville's lemma. And so we consider the quotient surface of Y by this canonical involution, and we study and we take the minimal desingularization of this And we are going to, and we studied quite in depth this situation. So we have this rational surface with this Z2 cubed action. And we take a minimal model. The definition is written there for this action. And using the fact that the action of G on W is induced from a free action on Y, I wrote X, but it's Y. We could describe very much. So we could find that this minimal model, we have a conic bundle structure. We could describe what is the fixed locus of this element there's just one element that sends the general fiber to itself. We knew the fixed locus, and then we could find it was not. We got to an impossible situation. So anyway, this I was doing this to show you that you see to characterize this surface with the maximum with pi 1 equals 9 was not easy, but was not so difficult. You go down 1, it starts being more difficult. And for instance, if you want to see what are the there are Campedelli surfaces with fundamental group of order 7. But if you want to show that every surface with k squared equals 3k minus 1 and no irregular has fundamental group of order 7, I'm not sure. So then this is the, oh, I'm going to finish a bit earlier. Sorry, I could have done more. But okay, this is the first thing. It would be a question if you can classify this. So you have Campedelli surface like that, but are there other surfaces? But again, it seems, okay, you know that the canonical, if you take the curve of order 7, then the canonical map of this curve must be birational, won't have, I think, base points, but then you don't have a good classification of these surfaces. So, sorry? The Campedelli surface. Huh? Of what? Of Campedelli's with Z7? I think there are the Miles examples. I don't know, right? Yes. Sorry. Yeah. So. Yeah. Yes, sure. Sorry, I'm still jet lagged. I've forgotten everything. So, okay, and also for k squared equals 3k minus 1 and pi r1 of order 6 by results of Daniel Nye. It's known that the symmetric group does not occur as the fundamental group of Campedelli. I don't know whether it occurs as fundamental group of others. Maybe not, I don't know. I didn't really think about that. Z6, yes, we know. Sorry? Yes, sure. Yes, I know, but the first person, yes, sorry. But it doesn't mean that for other characteristics it might occur, or no? maybe not. I don't know. I didn't really think. I put the question, but I didn't really think. So now there's another. This is kind of surface with PG equals 0, k squared equals 3. These are exactly surface in the borderline k squared equals 3 chi, have no irregular covers. So the question is if in that case the fundamental group is finite. So it's proven they have no irregular covers. Well, and finally this usual one, this usual question. If 3 chi less or equal than 4 chi squared lesser than 4 chi and no irregular at all covers, if the pi 1 is finite. So I don't know. So that's about what I had to say. I finished a bit earlier because I should have prepared more things.